All right, so this is our notes on optics, and we're going to learn about optics. And we learned about the energy of the sun. Now we're going to learn what does it do here on Earth, and how do we perceive those energies of the sun. So we're going to also talk about color. If you haven't already opened your assignment on optics and color in Google Classroom, please go do that now so you have access to the Cornell Notes template. All right, let's get started. Okay, so essential question here is, how do we see color? So that's what we're going to kind of answer in these notes today. So where does light come from? Well, it comes from the sun. The sun is a star located far away from Earth in space, and it provides energy in the form of light through a process called what we call nuclear fusion. And nuclear fusion occurs when two atoms that naturally repelled each other combine. So it's two of them coming together, and that energy that is released, because they're kind of hitting each other at a huge speed, that energy comes off and we get light, and we can also get heat as well. And so the sun provides energy that enables life on Earth. So light has energy, as we learned the other day. And we must follow the thermodynamics law that energy cannot be created or destroyed. So we get our energy on Earth from the sun, and that's where we get it. We can't create energy here on Earth. We can transfer it to a different type of energy, but we can't create it. And so the sun transfers its energy to us through radiation. And light travels very, very fast. It travels 3.0 times 10 to the 8th meters per second, about 300,000 kilometers per second. Okay? And it comes all the way around the Earth. There's a couple of properties that are strangeness, as I would call, of light. The speed of light is constant. It never changes. And nothing moves faster than the speed of light. And anything with mass cannot travel at the speed of light. So anything here on Earth cannot travel as fast as light. And light travels faster than sound. For example, you've probably experienced this during a thunderstorm. Thunder and lightning start at the same time, but you see the lightning before you can hear it. That's because light travels faster than sound. And so we see things based on a reflection of that light from the sun. That's how we see papers or anything, and it's perceived into our eyes. So that is how we see, is through the light of the sun. And there's a couple properties of light, which I'll just quickly go over. You'll learn more about it in chemistry, but light travels in waves. It also travels as a particle, and we see color because some light is reflected and other parts of light are absorbed. And what is this total light? Well, we call it the electromagnetic waves, or EM spectrum. And there are waves we can see, which are the visible light part here, and other waves we can't. We can't see radio waves, microwaves, infrared light, UV light, X-rays, or gamma rays, okay? We are going to just work here in the visible light, because that is what we can see and can experience. And so we can only see very, very tiny. It's just one little tick here, small part of the EM spectrum called the visible spectrum. And we view it as different colors, and those different colors have different frequencies and different wavelengths. Okay? So if we were to look to a prism, it would split the white light into all the visible colors like red, orange, yellow, green, blue, indigo, and violet, which we've all seen all over. And the color we see are the waves of that visible spectrum, so different frequency, wavelengths of the spectrum. So red is different from orange, and orange is different from yellow, and so forth. And the colors we do not see are the waves of the visible spectrum that absorb, and we actually see the ones that are reflected. And so white light is actually where all the light is reflected off, and that's why something looks white, and something that looks black actually absorbs all these different wavelengths. So the color an object appears is a color of wavelength that it reflects. For example, let's look at this red book, okay? White light comes and hits it, and it's all the different colors. And then why does it look red? Well, that is because it actually reflects that red, and it is the only one. So it absorbed orange, yellow, green, blue, indigo, and violet, okay? Only red light was actually reflected. Let's look at a couple other ones. So white light comes in. It's going to hit these pants. Give you a minute. What color is reflected? Well, if you said purple, you are right. How about this one? How about a white hat? So if white light comes in, what is reflected? Give you a second to get that one. If you said all the colors, you would be absolutely correct. Let's look at a few more. So we're going to look at white light's going to come in with all the colors. How about this shirt? What would be reflected there? If you said red, you're right. How about these pants? Why do they look black? What is reflected? Absolutely nothing. So black is actually absorbing all of the colors. That's why a lot of people don't like black cars. And why they get hot so fast is because they are actually absorbing all the different wavelengths of light. All right, again, a black shirt, white light coming in. And once again, why does it look black? Because all the colors are absorbed. How about these shorts? Why are they blue? Give you a second. It's because blue light is reflected, while everything else is absorbed. So that is how we see color. All right, so I want you to go back and process your notes. Go back and highlight any important information. Go back and make connections to your notes. You can write them in the left column. Go back and write questions you may have about your notes and write those in the left column. Use all of that to write a 3 to 5 sentence summary of your notes and turn them in. Well, that's our notes on color.